our third technical presentation of the 2021 school year. Hopefully we'll have a total of about 7 or 8 for you guys to give you guys the opportunity to meet different professional engineers and mathematicians. I'm actually trying to set up one for a mathematician also for you guys. So it should be a lot of fun today. This one's a little bit special for me, considering the fact that Amy, of course, is my daughter, and she has made us very proud, me and her mother, over the years, as she did not have the best opportunities, the best, I wouldn't say opportunities. She did not have the best grades in mathematics during high school. She struggled with math often. And so, but she pushed through it and did what she needed to do to become an engineer, going to Cal State Long Beach and joining their biomedical and electrical engineering program there. And so without further ado, this is Amy Fisher of Edwards Lifesciences. You are muted, Amy. Can you unmute yourself? I got to make sure that I didn't shut that off, or you can't unmute. You give me just a moment. My apologies. So I did participate. Hold on one second. Participants, allow them. There we go. Now you should be able to.
Okay. Yes. Now I can. Okay. Am I good to go?
Yep. You're good to go.
Awesome. Hello, everybody. As Mr. Fisher said, my name is Amy Fisher, and today I'm going to be talking to you guys a little bit about the work that I do at Edwards Lifesciences and why math is such an important role in the engineering field. So I'm going to start with a little bit of my background and my schooling, and then I'm going to give you guys a brief history of Edwards Lifesciences, what it is that we do, some of my day-to-day work, how we apply math in our day-to-day work here at Edwards, and why I chose biomedical engineering and why biomedical engineering is something that I feel like is an important profession and career to be a part of. So a little bit about me. As Mr. Fisher said, I graduated from Cal State Long Beach in 2016. I have a double bachelor's in electrical engineering and biomedical engineering. And I had multiple internships throughout college that were all based out of here in Orange County. And one of the cool things about that was because they were so close to home and school for me, I was able to have those internships turn into part-time roles that I kept during the semester. Which is awesome because most internships typically run like a 12-week course because you have a summer role and you're in between classes. But having that part-time experience to go on to gave me a lot more experience that helped me move on in my internships a lot quicker. And by the time I got to my last one, I worked part-time at Medipines for my entire senior year of college, and was able to roll out as a full-time engineer once I graduated and worked there for another year before joining Edwards Lifesciences. And at Edwards Lifesciences, if you guys don't know anything about it, is a medical company based out of Irvine, California. And one of the main things that we work on is the manufacturing of replacement heart valves that are used in the body and for medical procedures. So I'm going to talk to you guys a little bit about the history of Edwards. And we've been around since the 1960s, and it was originally founded by 2 men. We had an engineer named Miles Lowell Edwards and Dr. Albert Starr, who was a cardiac surgeon. And Miles Edwards was actually an engineer who developed fuel pumps for military aircraft. And as a child, he suffered from rheumatic fever, which is known to lead to a lot of heart problems as you get older. So he took an interest early on in trying to find a way to heal the heart. And because of his background and knowledge of pumps, and since the heart is essentially a big giant pump, he thought he would set out to create the first artificial heart and reached out to Dr. Starr for help. And that was in like 1959. And Dr. Starr was kind of talked to him and said, yeah, you know, artificial heart is kind of hard. Why don't we work on developing a valve as a first step? And by 1960, they had developed the first successful replacement heart valve, which was the Starr-Edwards valve, which you guys can see here. And this was a very simple mechanical design. It's a ball and cage design, and the ball would open as blood flows through, and then that ball closes when the blood flow stops, when the heart is pumping, and that helps control the blood. This was a super durable design. People actually still have this valve implanted. They've had it for over 50 years. But one of the issues with this was that because it was a valve that had metal parts, it required patients to take blood thinners. And when you're on blood thinners, that means you have to have a quality of life change, and you have to make sure that you're a lot more careful because you can have increased bleeding. So they needed a better option to work with because they didn't want to have people be on medication for their entire lives with this. So they kept working and instead thought, okay, what about if we had a tissue valve? And by 1975, they launched the first tissue porcine valve. And for those of you that don't know, porcine comes from pig. And the first porcine valve was an actual pig's heart valve that they had taken out of a pig because a pig's heart is very similar in size to humans. So they take it out, and what they do is they manufacture it to have this stent around it, and that stent is sewn in place where our heart valve typically would be in the human heart. And this worked seemingly pretty well. There's no metal like they had in the mechanical valve, so you don't need blood thinners anymore. But then they had an issue of durability where the mechanical valves, we've seen them last for 50 years. A pig's lifespan is only about 7 to 12 years. And the valves had a very similar durability in humans. So you would have to go in and replace them more often, which means you have to have another full open heart surgery to go in there, take the valve out, and put a new one in. So again, we needed something better. And they went back to the drawing table to look for something new. And by the 1980s, they had started using bovine tissue, which is cow tissue instead. And because cows have a much longer lifespan, they were using not the heart valves, because the valves are different sizes in cows. We're much more anatomically similar to pigs. But there is what is called pericardial tissue, which surrounds the outside of the heart. And what they would do is they would take that tissue and they would test it and cut it down into valve leaflets, which are the 3 different parts of the valve. And each one of those leaflets has to go through extensive testing to make sure they all have the same stress and durability, because those valves or those leaflets are going to get sewn together to be one final valve. So if you have one leaflet that bends under a different amount of stress than the other, your leaflets aren't going to close at the same rate, which means you can have regurgitation. So that pericardial tissue has to be extensively tested and engineered for everything to come together. And then we have our first bovine valve. And these valves last a lot longer. We've had them in patients now for like 25 to 30 years. And currently at Edwards, these are the only tissue valves that we continue to make. We stopped making the porcine valves in 2014, and the mechanical valve stopped in around 2007. So that's a brief history of our valves, and I'll kind of go into what we do with our valves now. And at Edwards, we have 2 main areas of focus for helping patients. And our first and primary focus, as you can see, is structural heart disease. And that encompasses all of the valves that we do, and it's the largest part of our business. So we currently have 2 different types of valves. We have surgical valves, which are implanted using open heart surgery. And we have what is called a transcatheter heart valve. And this is a valve that is implanted using a minimally invasive surgery, so you don't have to open up the full chest. We do have a third department of the company that also focuses on structural heart disease, which is our transcatheter mitral and tricuspid therapies department. And instead of working on replacing heart valves, they actually work on ways to go in and using minimally invasive techniques, fix a damaged valve. And Brian Murphy, one of our other engineers at Edwards, works in this department, and he will be giving you guys a detailed presentation on what projects we work on in TMTT in the upcoming months. So I'm going to start by talking about our surgical valves, and these are currently the gold standards for heart valve replacement. And we make these valves on our main campus in Irvine, and it's a pretty intricate process. Each valve has to be sewn by hand. underneath a microscope, like you see in this picture here, and it can take anywhere from 6 to 10 hours to make a valve. Sorry. And each valve is about 1,000 stitches. And to kind of give you an idea of how thick that pericardial tissue is, the needles need to be replaced after every 10 to 15 stitches because it dulls down the needle. So this is an extremely difficult process for our sewers to go through. And not only that, they have to use a single piece of thread the entire time. So if the thread breaks, move on. You got to go to another valve and that needs to be replaced. So it's a very detailed process to make these. And these valves are used for total valve replacement for the aortic and mitral valve. And it requires open heart surgery, meaning the surgeon has to cut you open through your entire chest, cut open your sternum to get underneath your rib cage. They have to stop your heart. They have to go into your heart and cut out your existing damaged valve and then sew this new valve into place. And this procedure can take on average anywhere from 2 to 4 hours for a cardiac surgeon to do. And just basic healing time for the patient can be up to 2 months and can take anywhere from up to 6 months before you're actually feeling like you're back to normal. So due to the extensive nature of this procedure, these valves are typically only given to low-risk patients who have a high chance of surviving surgery. So as you can imagine, sometimes that can be difficult because you have to be sick enough to require a replacement valve, but healthy enough for them to guarantee that you're also going to make it through surgery. So this was an issue that we dealt with for a long time. And for those high risk patients that may, like if you have somebody that's a lot older, grandparents, older people, and they have a very low chance of surviving that surgery, they just don't get a replacement heart valve. And that's one of the issues that we were trying to fix when we had our transcatheter division come around. So for those patients who are a high risk and are denied that option of a surgical valve, we now have a transcatheter valve replacement option. And our first transcatheter valve came out at around 2011. And up until last year, the FDA only approved this for high-risk patients because it was such a new valve and because it was such a new type of procedure. So now that we're actually gaining more traction and we have a lot more durability and reliability data, as of 2019, we are approved now to use this form of surgery on low-risk patients, which is a really great accomplishment for us. But as you can see, these valves look quite a bit different than our surgical valves. They do have a metal frame, and they are a lot more difficult to make. They take around 22 hours to assemble these valves. And the sewers and the assemblers that we have for these have to go through 6 to 9 months of training. And typically, because it's such a delicate process and it's so difficult to do, we only keep about 10% of the people that make it through that training that are able to stick around to manufacture these valves. And most of the time, those people stick around for a while. And some of our original valve sewer we have had working at the company since the 1960s and the 1970s, and they've been around for 40 and 50 years. Because once you know how to do it, we want to keep you around. But this procedure is done a lot differently. So with the surgical valve, you would have to, like I said, open up the chest, go into the heart. But sorry, guys. This valve is designed to be inserted via a catheter through the femoral artery. So as you can see here, this picture is the valve at full deployment size. And then this is the delivery system that we use to deploy the valve through the body. So the valve, as it goes into the body, is actually compressed down over the tip of the catheter, as you see it here. And once you have that small incision made in your leg, they feed this 6-foot-long delivery system through your femoral artery up into your heart, where they can then deploy the valve. And the metal valve expands and locks into place. And this procedure is much quicker. It only takes about an hour. And for well-trained cardiac surgeons, it's actually only about 15 to 20 minutes for them to do. And because you only have a small incision, recovery time is less than a week. So this really is a big difference compared to the surgical options that we have for valves. And that's why this is our main area of focus for Edwards, because with the data that we have coming in showing the reliability of these valves, it's keeping up to pace with our surgical valves. So we're expecting these to last just as long, if not longer. And one of the cool things about this is with surgical valves, you have to go in, take out the existing damaged valve, put the valve in. But for this one, you deploy this valve in right over top of the actual valve. So it just kind of pushes the valve to the side. And if you have a surgical valve fail, you have to go in again, cut it out because it's sewn in place. But with these transcatheter valves, this can actually be put inside of a surgical valve and deployed in its place without needing to remove the existing valve, whether it's a replacement valve or the actual valve. So there are a lot of upsides to it, which is good, and not as many downsides compared to the surgical valve. So we're hoping that this is going to be the next generation of valve moving forward. So I do have a video to show you guys about how this valve is deployed in the body. So after you have the incision into the femoral artery, you have the catheter that's fed up into the heart and comes over the aortic arch. And as you can see, you have the initial valve that is right here, and that's the damaged valve that the patient has currently. So once it's fed through, they have to have a lot of precision to get the replacement valve in a specific spot. And the reason why this is so important is because once that metal frame is locked into place, it cannot be moved again. So this has to be in the perfect position to be deployed. If it's deployed in the wrong spot, they do have to go in for emergency surgery and open the heart to get that valve out of place. So once it's in place, we inflate a balloon at the tip of the catheter that then opens the valve, deploys it, and they pull out the catheter, pull out the guide wire that helps keep it in place, and you have a brand new replacement functional valve. So it's a very, very quick procedure. And this is what the company is focusing on moving forward at this point, is creating these types of valves. So that moves us on to the next part of our company, which is where I work, which is our critical care department. And in our critical care section, we focus on basically monitoring all vitals that pertain to the heart during and after surgical procedures, as well as having products that improve blood flow throughout the body. So we also design catheters that go in very similar to the transcatheter valves, where you have a balloon catheter that can actually take out clots in the body. So we do those, but most of what we work on is sensors and monitoring. And in order to monitor what's going on in the heart, you really have to get into the heart. And one of the original products that paved the way for our critical care department is what we call a Swangans catheter. And it's actually kind of neat because if you watch any type of medical TV shows like House, Chicago MD, or We Know Whatever, they actually, Swangans is like a Kleenex term. So we hear it all the time watching shows, and it's kind of neat to know that, like, ooh, we did that. And that's a fun thing. But the Swangans is a catheter that's placed inside the heart, very similar to how the video that we just saw, where they make an incision in the femoral artery, and they put that catheter in the pulmonic valve, and that helps to measure arterial pressure and blood flow through the heart. And that's been one of our staple products for the last 30 or 40 years, and it's still one that we use today. But one other thing that we've been focusing on is trying to develop solutions that are less invasive for patients, and then making some monitoring screens and platforms that are going to encompass a wide range of sensors as well. So that brings us to what I work on the most, which is a lot of our wearable sensors and our Hemisphere platform. So our Hemisphere is basically this giant monitoring screen that takes in all of our sensors that we have in critical care to give a complete look of patient vitals to our clinicians that work in the hospitals. And it is compatible still with our Swangans catheters, and they're used regularly with our hemispheres, but are typically only used for high-risk procedures where we need the highest accuracy of those blood pressure values. So for lower risk or moderate risk procedures, we have different systems like our FlowTrack system, which also measures arterial blood pressure. But instead of having to put it into your heart, the FlowTrack gets inserted into your arm, similar to a traditional IV catheter, and we measure arterial blood pressure and flow in your ulnar artery in your arm. And for extremely low risk procedures, we have our Clearsight system, which was actually what I first started working on when I joined at Edwards. And that also measures non-invasive continuous blood pressure. And I think this device is really cool. I might be a little biased because I did work on it for such a long time when I joined. But if you've ever gone to the doctor and they take your blood pressure, typically they put a really big blood pressure cuff around your arm and they take your blood pressure for like that second. And one of the cool things about this is that big arm cuff is actually reduced down and it's put on the tip of your finger, and it gives a beat-to-beat continuous blood pressure measurement throughout the patient's entire procedure. And the reason why we only use this for low risk procedures is because it is not as accurate as what we're specifically measuring in the heart. But we are gathering more data and proving higher accuracy as we make improvements over time. And we are using it for now slightly higher to moderately risk procedures. And lastly, one of the newest sensors that we have is our Foresight sensor. And this one we had pulled in last year. It's a new sensor that we have, and this measures oxygen delivery to the brain. And we use this across all procedures. It's really great because one of the biggest issues that we have during surgical procedures is if patients are losing oxygen, that's definitely the worst thing possible. But there is no way for us to really know at the level of where their brain is to know how much oxygen is being delivered there. And as soon as they start losing oxygen to their brain, they're going to start losing bodily functions. So this is a very innovative way for us to do that non-invasively. And this is especially important because especially for pediatrics and neonatal surgeries or anything that has to do with infants, it's very difficult. They're very fragile. And we can't do a lot of these invasive procedures. So Foresight is one of the few sensors that we use for our in our pediatrics department at hospitals. So this will kind of lead me into what I do on my day-to-day basis, because as I said, I worked on the Clearsight cuff. But a lot of what I've been doing this last year is actually doing the board design that goes along with our monitoring platforms and designing some of the boards that goes into it, along with designing sensor test fixtures. So there's a lot that goes into the layout and design of these PCBs. And not only do we have the circuit aspects and the schematics that need to be put together, but all of that then needs to be designed and laid out onto a board. And that layout can be very time consuming, and it's an extremely iterative process sometimes, especially in the early design phases. So, these boards are made up of multiple layers, and we have hundreds of signals that have to be routed between components. And as you can see, we have this board down here, which seems to kind of not have as much space, but a pretty standard, looking outline. And then we have this board up here that has why is this whole space over here empty? There was a reason. But this one has a lot more space, but kind of all these weird nooks and crannies. And sometimes it can be difficult because we have to design something and we're working with our mechanical team because we have 20 of these boards that we have to fit into an enclosure, and they all have to fit together and be mounted in specific ways. And so when I talk about how I work cross-functionally with teams to design and assemble prototypes, on a day-to-day basis, I'm constantly working with my mechanical engineers, making sure that, there's nothing on these boards that need to change, because if you have, a mounting hole that's moved or a screw hole that's moved, it can cause a cascade of changes between my boards, somebody else's boards, now a whole enclosure design for the outside of whatever our monitor is. And that's kind of why I like some of the other aspects of my job, like when I get to design my own test fixtures, because then I have the freedom to kind of pick out my own board shapes and I guess be my own mechanical engineer. And I do have my electrical engineering degree, but on the job and because of the different internships that I've had, I've actually been able to get a lot of SolidWorks experience, and I have multiple SolidWorks certifications at this point. So if we don't have a mechanical engineer that has the time to help us, a lot of time for my team, which is our electrical engineering team at Edwards, I kind of get to play that role and build a lot of enclosures as well, and kind of get to do a break from the electrical engineering and kind of pick up some of the CAD design also, which I think is really fun. But that also means that then I have to be the one responsible for doing all the calculations and the analysis of how everything goes together, which can be a long process. So I know I said I would talk a little bit about the math that goes into this. And one of the things that we do when we have these giant mechanical enclosures is we have to calculate tolerance stack-ups, and each single part and each component, every single screw that we use has a tolerance in the dimensioning. And we have to make sure that worst case and best case scenario, everything is going to fit properly, not that we're assembling an entire prototype device and we go to screw something in and it breaks two things because there's too much stress or too much force being put on one area because we didn't account for those tolerances properly. But one of the main aspects of math that I do in my job would be for basic circuit analysis. And there's a lot of math that's involved in electrical engineering. We do it on a consistent basis, and down to the most fundamental level, we have Ohm's law, which is one of the most important equations that we use in electrical engineering because it relates voltage and current to resistance. And the further we dive down into circuit analysis, we have equations that help us simplify circuits that consists of multiple resistors and capacitors. Like in here, we have equations that help us break things down when those resistors are in series compared to parallel resistors in circuits. And so you can see a lot of this is just on the basic circuit analysis side. Then you get into the advanced circuit analysis, and we have a lot of differential equations. We have linear algebra that we have to deal with. So math is in a very important role, especially on the electrical engineering side of things. And it's not just for circuit analysis, but when we're also talking about sensor calibration, and like I said, I do work a lot with sensors, we have to make sure that they're all calibrated properly before we're using them either for testing in-house or definitely before they're going out into the field and being used on patients. So we're constantly doing 2-point or multiple point calibrations where we have to calculate the responses and find those slopes as compared to the ideal response that's specified with those sensors, and then calculate and program those offsets into our devices. And some of these products are calibrated during the manufacturing process. So it's just a one-time, it's done, and you move on, and that product goes out into the field. But we have other sensors like our heart reference sensor for Clearsight. And this is a height sensor that is supposed to be placed at the patient's heart, because when the patient is laying down, there is a gap in distance from the heart to the cuff on the finger. And this plays a difference because gravity affects blood pressure. So if the hand is lower than the heart, that's going to affect your blood pressure reading. And to make sure that we're getting the blood pressure at the heart level, because remember, we want everything at the heart, we have to calibrate that sensor each time we use it. Which means that, and over time, that sensor also drifts and we lose accuracy. So even in the field, before any measurement is taken, we have to have that sensor lined up with a 0-point reference to calculate that offset so that we know in our devices that the readings that we're getting for our doctors is the actual reading. So one of the last things that I want to talk about today is kind of why I chose biomedical engineering. I do also have an electrical engineering degree, and as you can see from everything that we do with the company, a lot of our valves are very mechanical in nature. So most of our valve department is a lot of mechanical engineers and biomedical engineers. And then what the people that I work with in our critical care department, we have electrical engineers, software engineers, And there's a wide range of majors that'll get you into the medical field. It doesn't just have to be a biomedical degree, but the biomedical degree does help you with the biology background. So that is something very important to keep in mind, if this is something that you want to do. But for me, the reason why I got into biomedical engineering, and I think for it's not just for me, but for all of my coworkers at Edwards, every day for us, our focus is how can we make patient lives better? And for me, that's what's driven me to want to work in the medical industry for a really long time. And I really do feel proud every day knowing that the work I do is impacting people across the world. And that to me is probably the best thing about my job, and is one of the best things about being a biomedical engineer. And engineering in general is always trying to find a solution to a problem. But in the medical industry, the problems that we solve save lives, and they're making people's lives better. And sometimes it's hard to directly see that impact with some of the work that we do. But one cool thing that our company likes to do is end our meetings with videos to remind us that the work that we're doing is always impacting people. And I have one of those videos for you guys today. So I am going to share that with you, and I hope it inspires you as much as it inspires all of us at Edwards. I don't know, Mr. Fisher, if I did my settings properly to have the video. So we're going to see. Can you let me know if you hear it when I play it?
I sure can. I sure will. Yep, there's sound. You're good.
Okay.
Clean and clear, no nicks. Screws are good. I think we're ready to go to the Bahamas. My name's Billgarde. I'm 59 years old. I live in DeLand, Florida. I've been fortunate to lead a very active lifestyle. I want to get up and go and make things happen. I enjoy flying airplanes, skiing, scuba diving, cycling, and that's a way I've chosen to live my life. Flying airplanes gives my wife and I freedom, the ability to see the world in a way that not everybody else gets to see it. And in order to support this adventure habit, I've recently started a parachute company with a friend. It allows me to combine my love of adventure with an actual business that helps support that. I first found out I had aortic stenosis by accident when I was being prepped for back surgery. I had no symptoms. Then last year I was in Bali and we climbed a 1,000-foot peak, and I found myself being very short of breath. My heart rate would go up to 125. I'd sit down, rest, drink water, and it took me 8 cycles of that to climb 1,000 feet. When I met with my cardiologist later, he said, "You're not just out of shape, those are symptoms of aortic stenosis, and it's now moved to severe. And you will need a valve replacement at some point in the future." That was hard to hear. I realized the things that could be affected by this situation. My family, my business, and the fear was very real. But luckily, there was a solution.
At Bill's age of 59, we'd consider a mechanical heart valve, which will last longer, but to avoid a potential stroke, he'd have to take blood thinners or Coumadin and follow a very dedicated dosing schedule the rest of his life. Plus, blood thinners would put Bill at a significant risk of severe bleeding.
Blood thinners would mean completely relooking at how I lived my life. If I were no longer able to pursue my passion, it would certainly impact my livelihood.
Tissue valves are a better choice for active people, but depending on the patient's age, they may not last as long with earlier valve deterioration, so I told him about the new Inspiris Resilia aortic valve. This valve is made with Resilia tissue. It's a bovine pericardial tissue with integrity preservation technology that actually blocks calcium buildup on the valve over time. The animal data on Resilia tissue is quite promising, and it could really make a difference for active patients. The Inspiris valve also has a feature called V-Fit technology.
And that was an easy, no-brainer decision. The surgery went pretty seamless, and now I'm 3 months out, and I feel fantastic.
Southerly course?
Yeah, let's go fly. I'm exercising regularly. I'm taking on tons of challenges, meeting new customers, and I feel great. Getting back to flying has been amazing. It's wonderful to be able, after the heart surgery and recovery, to get back in and have that freedom to go. But sometimes it's not enough, and I just gotta jump. If you're gonna jump, you better have a good parachute. And we make fantastic parachutes, and that's super rewarding. I could not even imagine what my life would be like on blood thinners. So I'm grateful for this amazing product and what the new Inspiris valve has done for me.
All right.
All right.
That is the end of my presentation, guys. Thank you so much. I hope you enjoyed it.
We do have some questions for you. Can you go ahead and stop sharing?
Yes.
Perfect. And then I will probably call out them to read their own messages. So let me open this up. Adrian Bayadas, do you want to go ahead and ask your very first question? You actually asked it at 1:12 if you want to go back into the chat.
I asked for the valves, the first one. I was asking, why does it have to be hand sewn?
I don't know specifically why it has to be hand sewn. I think it's just because it's so intricate and because there are so many tiny stitches. It's probably very difficult with the curvature to do it on a device that has to sew it into place. And because the threading all has to be one piece, it probably has to have a lot of oversight to be looking over to make sure the quality check is done properly. But what I can do is get an actual answer for that question and get back to you about it. I don't know why exactly we do have it hand sewn, if there is another specific reason, but I would assume it's to make sure that we have full quality control over everything that we do.
Amanda, you asked a question also. Would you like to, at 123, would you like to ask it?
Yes, I asked about the valves as well. If the body ever rejects the valve?
So typically with the tissue, the type of tissue that we have, I don't know. I've never really had anybody talk to me about whether or not the valves are rejected. They do go through a lot of, we do have a lot of like biomaterial science that goes into it and making sure that it's compatible with the body. I'm not sure. Typically, I don't hear anything about whether it's rejected by the body. I think it's typically accepted.
Excellent. Mr. Ramos, would you like to ask your question?
Hi, my name is Michael Ramos. I'm a senior, and I'm actually interested in the same career pathway that you took.
Okay.
So with that being said, what does your work environment look like? Is it versatile? So do you work at a desk one day, or the next day you might work in the lab, or the day after that you work in like a meeting room talking and having discussions?
Yeah, totally. I can talk about that. So right now, it is extremely versatile. Sometimes I'm at my desk at home. Other times I'm at my desk in the office. But on a normal basis, yes, it is very versatile. There are days where I'm doing computer work and I'm at my desk most of the time. There are some days where I do have an extensive amount of meetings and I'm in and out of conference rooms and meeting with people when we're in the office. Right now, I'm not going into conference rooms. But then I also do a lot of lab work also. And we're actually one of the few teams that have cubicles and designated lab space for us because we do have labs. Our labs are used for a lot of testing. I don't keep all of my testing equipment at my cubicle space. So it is something where I am moving around a lot and I'm doing a lot of different tasks. It's not just doing one thing at a time, especially when it comes to the board design work specifically that I do. Because a lot of that work is done on the computer. So I'll spend a couple weeks on the computer and then we get the boards fabricated and sent in-house. And then we have an extensive amount of testing that we have to do to bring up those boards, make sure that we're getting all the signals going to the right places, all the voltages are working properly. So that does change on a day-to-day basis what we're doing. Does that answer your question?
Yes, thank you.
Michael, you had another question. You want to go ahead and ask it already?
Yeah. So I asked, how did your degree in biomedical and electrical engineering help you or prepare you for this job? When you got this job, did you work with things that were familiar with you because it was material you learned in college, or did you encounter a lot of things that weren't really covered in college?
Great question.
That's a really good question. So a lot of the stuff that had prepared, so I'm kind of going to give it a different or I don't know, maybe it's a weird answer. But my college experience helped prepare me for my internships. And my internships was really what prepared me for the work that I was doing. So college gives you a lot of the fundamental basics that you have to know for your jobs, but it's really the work experience that you're getting that is going to help you with your job experience the further you go into your career. So the electrical engineering helped me with my first two internships, and the soldering experience that I got in school helped me with that, and being able to work on projects where I can build things up, like for my senior design and class projects and stuff like that. And once I got my internships, a lot of the work that I was doing there kind of paved the way for me to learn more things. Like, for example, a lot of the CAD design stuff that I learned as an electrical engineer, I did not learn that at school. I learned all of that on the job. So the electrical engineering aspects of my schooling help me a lot now. But when I first started working at Edwards, I've done everything from software programming to algorithm analysis, and I've done CAD design, electrical engineering. So the schooling helps you get to where you want to go, but a lot of the experience that you're getting is also from your internships and just the work that you're doing on a day-to-day basis. And employers know that also. So they never hire you expecting you to know everything. They want you to have the background so that you have the opportunity to grow and understand those concepts that they're going to show you at your job. And that's the important aspect about school, is to understand just the fundamental concepts of what you're learning, because that's going to help you as you dive down deeper into the applied, like into the application of how to do that in the real world.
Nice. JC Kim Przinski, do you want to ask your question?
Yes, I would like to. How much does a valve usually cost?
That is a very good question, and that is not one that I researched. So I don't know. I would say, I'm definitely going to say, I don't know the exact cost. I do know it's in the ballpark of a couple tens of thousands of dollars just to have the valve itself. That's not including the procedural cost, which if you have an anesthesiologist, that's going to be a lot more money. And then to hire a cardiac surgeon is a lot more. So the valves itself, I believe, are, I don't want to say an exact number because I don't know, but I believe, like I said, in those tens of thousands of dollars. And then, I mean, to go through your full procedure can be a couple $100,000 once you incur the other medical expenses that you have.
Thank you.
Adrian Bayeris, you had a second question. Did you want to ask it?
Yeah. To get into biomedical engineering, did you have to get a medical degree, an engineering degree, or do you collaborate with doctors?
So we do a lot of doctor collaboration, but it definitely helps to have some type of medical background. So having my biomedical degree allowed me to have like somewhat of a biology and physiology background because I took those classes in college. So it does help in that way. But we have a lot of engineers that do not have a biomedical degree. They're just regular software engineers, mechanical engineers, electrical engineers. And depending on what aspects you work on. Now, if you're working in the valve department of our company, most of those engineers are biomedical engineers because they need to have that physiology background. But to get into medical engineering in general, sometimes you don't have to have it. And they also know that some of this is a very specific knowledge base. So when I first started working at Edwards, which is a cardiac company, I didn't really have anything more than just a basic knowledge of how the heart functioned because my previous medical device company was a respiratory company. So I knew all about lung function, but I didn't know as much about heart function. And they know that when they hire you, and they're also there to help train you because they want you to know the specific aspects of the job. So if you're able to perform on the engineering side, they'll teach you the biology. And that's what happens with a lot of our engineers.
Ravino Macadon, do you want to ask your question?
Oh, sorry, wrong button. But for the catheter valves, are they lifelong or do they need to be replaced over time?
For the transcatheter valves or the surgical valves, or either?
Either.
So they do right now only last around 25 to 30 years. So for our surgical valves, for both of them, sometimes they do need to be replaced depending on how old the patient is. With the surgical valves, for them to be replaced, most of the time they have to go in through another open heart surgery and then take out the valve because it is sewn into the heart and then put it in. One of the best things about our transcatheter valves is because it's a little bit thinner in profile because it has that metal frame. If you have a transcatheter valve that hits the end of its lifetime, they just have to deploy a new valve in and they can put a valve inside of a valve and it just gets sit inside that new one and it works just as well.
Wow.
All right, thank you.
Chris Caracosa, do you want to ask your question?
Yes, actually I have two questions.
Okay.
Sure.
For the first question, how big is the transadherer valve compared to the surgical heart valve, and how do they hand sew it when it's like as small in its size?
So they are typically around the same size, and the reason is because our valves are made in multiple sizes to make sure that they fit multiple heart sizes. So everybody, just as we all have like different heights, different hand shapes, everybody's hearts are different size, which means we have valves that are different sizes as well. So our transcatheter valves and surgical valves are around the same diameter because they have to fit in that same valve space. And that is why, because they're so small, they are all made under microscopes. So it is very, very tiny.
All right,
Alexis,
yep. Yeah, for my second question, so let's say if for the surgical heart valve, if it's misplaced, do they unsew it or do they put the transcatheter valve to replace it?
So typically the surgical valves, I don't believe they have an issue with it really being in the wrong place, only because they're in the heart putting it there in the first place. So they have a better, they definitely have like more sight as to what's going on because they're physically there looking to make sure that it's done properly. So when those are sewn in place, they're typically put in the right place because the doctor's right there looking at it. The transcatheter valves, the reason why it's so hard, which is something that I didn't show on the screen, is that when those are deployed, they are only using fluoroscopy, which if you don't know is basically a 2D version of an X-ray. So they're only having a black and white 2D video image of that heart. So they can see basic shadowing, which is why it takes a very skilled cardiologist to do these procedures. But they have to be able to use that X-ray image to see where exactly that valve is, where the existing valve is, and so that they can deploy the replacement valve. So it's a little bit trickier to do those, which is why we prefer to have trained surgeons who are trained to do those procedures, do them more often. But that is why that one has that little stipulation where it's very critical for them to make sure it's put in the right place.
All right. Alexis Contreras, would you like to ask your question?
Yes. Is this procedure only available in the US?
No, it is not. It is available worldwide. We actually have manufacturing plants all throughout Europe and also Israel, and we do these procedures everywhere.
Michael Quintero.
So you mentioned that the transcatheter valve, you can, if it's nearing at the end of its lifetime, you can just put another one in. Is there a certain amount that you can't put any more in and you need to go into the heart?
I don't know if there's a certain amount. I know we already have instances where we have done double of the transcatheter valves. We actually had a very interesting case in Israel earlier this year where we had somebody who had a valve area that was a little bit too big. So we had to double up because we didn't make a valve as big as their opening. So I know for a fact that we can do two. And if these are valves that last anywhere from 25 to 30 years, I don't imagine that you would need more than two, depending on at what point you're getting the transcatheter valve in your lifetime. But I'm not sure. That's something that I can also check on and get back to you guys. But I know for a fact you can do at least two.
Ronald Encanto.
I was wondering, are there any signs or signals to show that you might need a heart valve?
So, I mean, two of the biggest issues that would cause reason for needing a replacement heart valve, like as we saw in the video, is aortic stenosis. And that is when the valve leaflets start to calcify and the valve doesn't close all the way anymore. So that would cause a lot of valve regurgitation or regurgitation of blood flow going back and forth through the heart, which isn't good. There are also congenital heart defects or heart diseases that you can have from a child. And as you get older, those heart defects can cause more problems. And so they would need to go in, and it can be as much as like you're missing a valve. There are some times where you're supposed to have a valve with 3 leaflets that only have 2 leaflets, so it doesn't close all the way. And so you need to have a 3 leaflet valve put in place. But typically aortic stenosis, I believe, is the biggest reason why we have it, or why we would need to put it in. It's basically anything that's just causing damage to the valve itself, any disease or disorder.
All right, Letty Patino.
Are the surgical valves constantly being innovated, or does it stay the same until a new problem with the valve arises?
No, we're constantly still innovating our surgical valves to try to figure out how to make them better. It's just something that, because it's a staple part of the industry, there aren't many changes, but like as you saw, the Inspiris Resilia valve is actually one of our surgical valves, I believe. And they're trying to find ways to make the tissue to reduce calcification on the valve to make sure that you're not having long-term issues while you're using it. So they are still working to do to do things that improve them. There's always room for improvement. And we are missing our moderator.
I'm coming back right
Come
now.
back.
Sorry.
Come back.
All right. Mary Lou.
Okay, so in your previous slides, you were talking about the finger cuffs, right? And how it's not yet too accurate. So I was wondering, like, what type of tests or ideas do you have to improve the accuracy?
So we are working on, I guess, some different ways to do it. I think one of the biggest reasons is that because there's a delay that comes from the actual heart, when we're talking about accuracy, it's just that from the heart to the finger, there's a bit of a distance. And there's always going to be less accuracy when you're talking about minimally invasive to non-invasive, or non-invasive wearables to fully invasive wearables, because you're getting it from the direct source. But we are continuously working on algorithm improvements to figure that out. And we run testing with our Swangans catheters and with our flow track systems as well to do comparisons to see if we can always make improvements with that. And we actually have a full team in Amsterdam that's currently looking at different ways to improve that cuff for us, to see if we can have whether it's improvements for how it fits on the finger. And that's also another reason, is because the wearables, sometimes it can be user error and if it's put on wrong. So there's different ways that we're looking at, and we're running a lot of different use case tests to see how it's used in the field, and just how we can improve the sensors or find better sensors to use as well.
Vanessa, you have a question?
Hi, Ms. Fisher. Yeah, I have a question for you. You said that you worked on the Clearsight project, right? When you first came to Edwards. What were the kind of challenges or difficulties that you faced when you were working on that project?
So one of the things that I had we had worked on, and it was actually something that was in line with the Clearsight project. I had ran a lot of testing for Clearsight, and I was working on a cuff. I was working on a similar cuff that was going to have a smaller profile and be a little bit easier to use, and was transportable, because our Clearsight system, the cuff looks small, but when you're talking about the entire pump system, because it is a pump and it does have to inflate so I can calculate blood pressure just like a regular brachial cuff, we were trying to find a version that basically could be traveled through the hospital with the patient instead of having to have this whole system on a large IV pole. And I mean, a lot of the issues that we come across when we're dealing with these things is making sure we're trying to find the right sensors and being able to have everything work together. Sometimes we have sensors that, you know, aren't as accurate as we would hope they would be. And we also have like design failures where we think, you know, this is going to be a wonderful mechanical design, and we get it into nurses and doctors' hands and we have clinicians work with it, and we have a lot of issues because it's not as clear to use as we thought it was. And then we have a lot of use case error, like I was talking about, which can cause limitations and cause accuracy issues. So on the development side of things, definitely it's a lot of iterations between going through different types of sensors, seeing what works the best and seeing what works best with everything designed in the whole system. And then making sure that it's also very easy to use, because if we have something that's not easy to use for our like clinical counterparts, then it's going to be difficult to implement in the field, and that's going to cause issues for us. And we have had products that get all the way up to that point where we're about ready to release, and it just seems like it's a little bit too difficult, and then we have to bring it back and then rescope our entire use case scenarios to make sure that they're easier to use for clinicians.
Thank you.
Mark Abelabor, you have a question?
Yeah, how do you determine if a patient is too high risk to undergo heart valve replacements?
That is a very good question. It is something that I typically think a lot has to do with age and has to do with their medical health. So for instance, if you have somebody that's in their 50s and 60s, is seemingly pretty healthy, except for the fact that they do have some type of heart cardiac issue that will require a valve replacement. If you talk to a doctor and they think, okay, this person is going to be fine, they're going to fully recover from surgery, that would be great. But when you're talking about patients that start having heart problems late into like their 70s and 80s, if they have other medical problems, that's going to limit how well they can do under an anesthetic. Then that's going to make them a higher risk. So it really is looking at how well they're going to make it out of surgery and the medical risk of them basically not making it through, because especially going through open heart surgery, it's a lot of physical trauma. You have to cut all the way down the chest, and then it's kind of weird, but they take these cutters and they really have to cut open your sternum and your rib cage, and all of that has to be put back together. So the older you get and the less of that you can handle, I think is really what the issue is. A lot of our higher risk patients are a lot older or have pre-existing medical conditions that would severely limit how well they can do in surgery.
All right, we'll take two more questions. One of them is going to be from Adrian Bayaris. Go ahead.
Would medication affect the heart valve like in the future?
What do you mean? Can I ask for you to clarify maybe?
Like medication that affects like heart rate, like antidepressants, I think.
I don't really know a lot about that. I don't know what specific medications would cause a lot of problems. Yeah, I don't really have a good answer to that question. I'm sorry.
All right. Any other questions, guys? One final question from anybody? All right. Well, then that will be it at 2 o'clock on the nose. Can't get any better than that. So it's a perfect 1 hour. I do appreciate all of you participating in this today.